Hello everyone, welcome to our presentation, Unit 4, Transformation by Trigonometric Formulas and Inverse Trigonometric Functions. Here you still needed to review your differentiation formulas for trigonometric and inverse trigonometric functions, as the integration formulas have been derived from here. Review also the common trigonometric identities as they are used in simplifying functions. Pay attention specifically of the algebraic signs of the derivative so that you will not be confused with the signs later on. This module will be containing the introduction and bridging of differential calculus to integral calculus. It should be understood that all the differentiation formulas you learned in differential calculus are also the same formulas that you will need to integrate the functions correctly. Also, the first set of basic integration formulas are included also in this module, and how you can use them to integrate common functions. There is a proper procedure for solving each type, and they are clearly demonstrated here. Trigonometric integrals also involve algebraic operations on trigonometric functions. You have already learned how to evaluate some trigonometric integrals. We will now apply these formulas, including the trigonometric identities you learn in trigonometry. We needed them so that we could evaluate the integrals, especially integrals involving products of powers of trigonometric functions. And usually these trigonometric functions cannot readily be integrated just by using the power formula. We really have to use this transformation by trigonometric formulas and inverse trigonometric functions. There are trigonometric functions which cannot be readily integrated by the power or by the logarithm formula. So there is a need for us to apply transformation. So we will begin with products of sine and cosine, and then we will try to distinguish the different cases in this module. The first case, which is case 1, involves the integral of sine raised to n of x dx, or the integral of cosine raised to n x dx. The condition is that our exponent here is a positive odd integer. So n is a positive odd integer. The first thing to be done is to factor. For example, if sine raised to x dx has an exponent of n, then we will convert or factor out, wherein we could write here sine raised to n minus 1, and of course the other one will be sine x dx. It follows for cosine raised to n x dx. And the next step is we will be using some of the transformation formulas, or the common trigonometric identity for the square of sine and the square of cosine. So sine squared x is equal to 1 minus cosine squared x, and cosine squared x is equal to 1 minus sine squared x. And then after that, we will now integrate the resulting function. Let us have this example. We have here the integral of cosine cube x dx. So again, the first thing we will factor out. So we could write this as cosine squared x times another cosine x dx. It will still be cosine cube x dx. And we will apply now the trigonometric transformation or identity for cosine squared x. Cosine squared x is equal to 1 minus sine squared x. Substitute that into the integral, and then we get the integral of the quantity 1 minus sine squared x times cosine x dx. And after which, we expand our integral or our expression. So here we get integral of cosine x dx minus the integral of sine squared x cosine x dx. From here, we could use the general power formula. Usually, in all cases, for case 1, we apply the general power formula to simplify our final expression into a final answer. It is the GPF. So for the first term, we factor out. Second, we transform by using the trigonometric identities. And then the third, we are now ready to integrate. Usually, case 1, we just simply use the general power formula. So your answer here for the first expression is the integral of cosine x dx is sine x. And then the second term, we just simply apply the general power formula. So it becomes minus sine cube x all over 3 plus the arbitrary constant c. Let us try the integral of sine raised to 5 of x dx. First step is we factor out. We could write this as sine raised to 4 of x sine x dx. And we use our transformation formula that 1 minus cosine squared x is actually sine squared x. And then we raise that to 2. It will still be the same as sine raised to 4 of x. And of course, we multiply sine x times dx. Next step is we expand this binomial. So expanding, we get here 1 minus 2 cosine squared x plus cosine raised to 4 of x if we expanded this. And then we will multiply sine of x dx. After that, we expand further. So the first term becomes integral of sine x dx plus 2 times the integral of cosine squared x times negative sine x dx. What happened here? The differential of cosine x is negative sine x dx. So we introduce negative 1, and then we introduce also the correcting factor before the integral sign, which is negative 1. A negative 1 and then a negative sign makes this positive. And for the third term, it becomes negative cosine raised to 4 of x times negative sine x dx. So the same explanation, the differential of cosine x is negative sine x dx. So we introduce negative 1, and we introduce also a negative 1 just before the integral sign. Since this was formerly positive, it becomes negative here. So now we're ready. We will just use the trigonometric formulas for the first term. Second term will be the general power formula. Third term still the general power formula. So our answer, final answer, the integral of sine x dx is negative cosine x. Here at the second term, it becomes 2 cosine cube, that will be 2 plus 1 all over 3 of x, minus cosine raised to 5. Why? Because that is 4 plus 1 all over 4 plus 1, which is 5, plus our arbitrary constant c. The second case involves a sine and a cosine in our integrand, where at least one of the exponents will be odd. So it is possible that it is the exponent of sine to be odd, or it is the exponent of cosine x will be odd, or the other one is odd and the other is even. The first thing is still we factor out the function with the odd exponent, and then we will use now transformation. We will still follow the same procedure. And again, we will be using the trigonometric identities or trigonometric transformation, wherein we can convert sine squared x and cosine squared x in terms of the other constant. And I repeat, we will be transforming the term with the odd exponent. So if n or the exponent of sine is odd, we will transform sine function. But if it is m to be odd, we will transform the cosine function. But if both n and m will be odd, it's a matter of choice. I always call that the theory of mini-mini. It's just simply mini-mini-minimo. So, again, I repeat, you transform the function with the odd exponent. So let's try number 3. The integral of sine cube x times cosine raised to 4 of x times dx. Again here, if you notice, it is the exponent of sine that is add. So that is what we factor out. And that is where our transformation will come in. So sine squared x times sine x times cosine raised to 4 of x dx. Now we will transform sine squared x. That becomes 1 minus cosine squared x times cosine raised to 4 of x. And then we have now sine x dx. Next step is to expand. Expanding, we get the first term to be the integral of cosine raised to 4 of x times the sine of x dx minus cosine raised to 6 of x sine x dx. And if you notice, we will still be applying here the general power formula. If we will be introducing our constant into the integrand together with the correcting factor just before the integral sign, we see here that the differential of cosine is negative sine x dx. We introduce negative 1. And then the correcting factor just before the negative, just before the integral sign, which is negative. And for the second term, still the same. The differential of cosine is negative sine x dx. So we introduce negative 1 into the integrand, provided we introduce a negative sign just before the integral sign. So the second term, if you notice, we have a negative and a negative number, makes it positive. So now we're ready applying the general power formula. The first term becomes negative cosine raised to 5 of x over 5. The second term becomes positive cosine raised to 7 of x all over 7 plus the arbitrary constant c. Let us proceed to case 3. For case 3, this will be integrals involving still sine alone, cosine alone, or together with a sine and a cosine. The condition now, both m and n are positive even integers. So if both will be even, we have a different method. The first step is we will factor out in a way that we will reduce our sine function. If it is the sine function that we wanted to simplify first, we will write that as sine squared x, and the whole quantity will be raised to n all over 2 dx. We will be using the trigonometric identity or trigonometric transformation for sine squared x will be equivalent to 1 minus cosine 2x over 2. What about if we wanted to simplify the cosine function whose exponent is also even? Well, it will still be the same. We will express cosine raised to nx dx in terms of cosine squared x, provided the whole quantity will be raised to n over 2. And then we will be using the transformation identity or transformation formula for cosine squared x. That becomes 1 plus cosine 2x all over 2. And after that, we can factor out, and then we will be using both the trigonometric identity for sine squared x and cosine squared x using the double angle identities. Let us try the fourth illustration or fourth example. The integral of sine squared x dx. Well, it's obvious our exponent is even, so we will be using a different type of trigonometric transformation where sine squared x is equivalent to 1 minus cosine 2x all over 2. If we expand, we get here negative 1/2 times the integral of dx for the first term. And for the second term, it's still negative 1/2, but it will be times the integral of cosine 2x times dx. The first integral or the first term will be just applying the properties of integrals. So it will be 1/2 of x. But for the second term, if you look at our angle, cosine 2x, it means 2x is the angle. If we take the differential of 2x, that is 2 dx. So it means we have to introduce 2 into the integrand, provided we will introduce its equivalent correcting factor, which is 1/2, to be placed in front of the integral sign. But we will not forget, we have to include negative 1/2 as the original constant found in the expression. So now here we could proceed just by applying the trigonometric formula for the integral of cosine. We get a final answer of 1/2 x minus 1/4. The integral of cosine 2x is sine 2x. That is why the second term is negative 1/4 sine 2x plus the arbitrary. If we will take the integral of cosine raised to 4x dx, we could write that as cosine squared x, and the whole quantity will be raised to 2 times dx. And if we will be transforming cosine squared x, that becomes 1 plus cosine 2x all over 2. And if we expand the integrand, the denominator is 2, so we raise that to 2, it becomes 4. It is a denominator and it is a constant, it becomes 1/4. We place that just before the integral sign. The numerator, which is 1 plus cosine 2x and the whole quantity is squared, if we expand that, it becomes 1 plus 2 cosine 2x plus cosine squared 2x dx. The third term of the integral, which is cosine squared 2x, could be trigonometrically transformed using the identity introduced, wherein we could write cosine squared 2x as 1 plus cosine 4x all over 2 from the given identity, which is cosine squared 2x. And the third step is to expand further. So once we expand this, we will be having a total of 4 terms. The first term will be 1/4 times the integral of dx. The second term is 1/2 times the integral of cosine 2x dx. And the third term becomes 1/8 times the integral of dx. Fourth term becomes 1/8 times the integral of cosine 4x dx. So if you notice, we could directly integrate each of the term using properties of integrals and trigonometric formula for integration. So if you notice, the first term will simply be 1/4 x. For the second term, we have to introduce 2 into the integrand and a correcting factor of 1/2 just before the integral sign. For the third term, that is simply 1/8 x. And for the fourth term, that will be introducing 4 into the integrand and 1/4 as the correcting factor. And then that now becomes a final answer of 3/8x if we add the 2x terms plus 1/4 sine 2x, and then the other one is 1/32 sine of 4x plus c. Case 4 involves tangent and cotangent in the integrand. Here our condition, n is a positive integer. So it may be odd, it may be even. So n, I repeat, is the exponent of our tangent or cotangent function found in the integrand. The first step is we will factor out tangent x dx will be equivalent to tangent raised to n minus 2 times tangent squared x dx. And then after that, we will be using the transformation formula for tangent squared, which is secant squared x minus 1. Again, if we have a cotangent, it will be the same. We have to bring out the cotangent squared in it, and then we will be using the transformation formula for cotangent squared, which is equivalent to cosecant squared x minus 1. So to illustrate that, we will be having the integral of tangent cube x dx. So we will bring out a factor of tangent squared. So that becomes tan x times tan squared x dx. And we will be using the trigonometric transformation for tan squared x, that is equivalent to secant squared x minus 1. We expand this. we get the integral of tangent x secant squared x dx as the first term. And the second term becomes minus the integral of tan x dx. If you notice in the first integral, the differential of tangent x is exactly secant squared x dx. And for the second term, we will just be applying trigonometric formulas. So we get here, applying the general power formula for the first term, we get tangent squared x over 2 plus the ln of cosine x plus c. For the integral of tangent, if you remember, there are two. It could be ln of secant x or the negative ln of cosine x. For this particular problem, you may convert this into secant or cosine. That will be depending on you. But here, I just had chosen negative ln cosine x as the integral of tangent x because this is negative. The second term is negative, and then the integral in terms of cosine will also be negative, so that at least the final answer is positive. For number 7, if we will take the integral of cotangent raised to 4 of 3x dx, then we will be factoring out the cotangent squared. So we have there a cotangent squared 3x and another cotangent squared 3x dx. Here, we have to transform one at a time. So first, we will be transforming one cotangent squared, wherein cotangent squared 3x is equivalent to cosecant squared 3x minus 1. Now, let us expand. Expanding, we get here the integral of cotangent squared 3x times cosecant squared 3x dx. And our last term will be minus the integral of cotangent squared 3x dx. The differential of cotangent 3x is actually negative 3 cosecant squared 3x dx. It means we have to introduce negative 3 into the integrand, provided we will also introduce its equivalent correcting factor, which is negative 1/3, to be placed in front or before the integral sign. And for the second term, if you notice, cotangent squared 3x dx, we will again transform that using its trigonometric identity in terms of cosecant squared 3x, wherein it becomes cosecant squared 3x minus 1 for the second term. And we're now ready. We could integrate the first term. So the first term, by applying the general power formula, it becomes negative 1/3 times cotangent cube 3x all over 3. And if we will expand the second term, it will become two terms already. So expanding, we get here negative 1/3 times the integral of cosecant squared 3x times 3 dx. So at the same time, we had corrected our integrand by introducing also a correction factor, which is negative 1/3 before the integral sign. And for the second term, once expanded, we only get their positive integral of dx. And the positive integral of dx is actually simply x. So there is only one term there that must be integrated. It is the second term. And at the same time, we simplify the first term and we could get already our final answer. The first term is negative 1 over 9 cotangent cube of 3x plus 1/3. And then the integral now becomes cotangent 3x plus x plus c. And that will be the final answer. We have another case, in this case 5. Case 5 is similar to case 4 regarding cotangent and tangent. For case 5, it is about secant and cosecant. Here the condition, if both integers or exponents will be positive, even integers. The first thing is to factor out, and then after factoring out and bringing out the secant squared or the cosecant squared from the integrand, we will be using these transformations. Secant squared will be tangent squared plus 1, and cosecant squared will be cotangent squared plus 1. Let us have an example. If we have the integral of cosecant squared x dx, we will factor out the cosecant squared x dx. We will do it one at a time, step by step. So that cosecant squared x dx will be transformed into cotangent squared x plus 1, which you can see here in the first line of solution. And after doing that, we expand our cotangent squared x plus 1 and the whole quantity squared. So expanding that, we get here cotangent raised to 4 of x plus 2 cotangent squared x plus 1, but we have to multiply that by cosine squared x. And that will be our integrand for the second line of solution. And we expand further. Expanding, that will be the integral of cotangent raised to 4 of x cosecant squared x dx plus 2 times the integral of cotangent squared x cosecant squared x dx, and the last term will become the integral of cosecant squared x dx. We could integrate directly by introducing our correction factor immediately so that you could simplify at once. Like in the first term is, if we take the differential of cotangent, that is negative cosecant squared. That is why the first term of the answer is actually negative cotangent 5x over 5. For the second term, it will still be the same, but the exponent is just simply 2. So still, the differential of cotangent is negative cosecant squared x dx. That is why the second term is negative. And for the third term, we will just use simply trigonometric formula. The integral of cosecant squared is actually negative cotangent. So our final answer, just finalize that. We will have a negative cotangent raised to 5 of x over 2 over 5 minus 2 times the cotangent cube of x over 3 minus cotangent x plus c. So this is all about trigonometric transformation, and I'll be giving concept checks also and assignment, and I'll be posting now the next quiz. It will be quiz number 2, and the deadline will be June 27. Let me just remind you, the deadline of all the requirements for concepts 1, concept 2, assignment 1, and quiz 1 will be today until 11:59 p.m. So ladies and gentlemen, I hope you're still doing well. Concentrate, and as I have told you, you have to focus on integral calculus. Do not waste your time. Do all the requirements that I will be giving so that at least we could finish this module. So ladies and gentlemen, I will see you in the next presentation.